Hello and welcome back for another video. In this video, we're going to be talking about logarithmic functions. This is the third section in the chapter on exponential and logarithmic functions. We're going to find that logarithms are actually the inverse functions to exponentials. Now, exponentials, remember, kind of look like this, or they kind of look like this. And they grow very rapidly, or they decay very rapidly. It turns out that if you swap the x and y variables in a one-to-one function, you get the inverse. We've looked at this before. So now what we're talking about doing is taking an exponential function and switching out the x and y values. And this creates what's known as a logarithmic function. Now, there are lots of things in the real world that function on a logarithmic scale. For example, the pH of a system or a liquid is a logarithmic scale. So when you're talking about how acidic something is or how basic something is in chemistry, you're actually using a logarithmic scale. You're also using a logarithmic scale when you talk about earthquakes. We use the Richter scale, which is actually a common logarithmic scale, base 10. Now, what does that mean? Well, if we talk about an earthquake that is a magnitude 5.0, and we compare it to an earthquake that is a magnitude 6.0, the difference between a 5.0 and a 6.0 is 1 unit. But that 1 is actually the power on base 10, which means that the 6.0 earthquake is 10 times more powerful than the 5.0 earthquake. Now, if I take an 8.0 earthquake, which would be mind-blowing, and compared it to the 5.0, that is a difference of 3. So that would be 10 to the third, all right? So that would be, gosh, that would be like 1,000 times more powerful. So an 8.0 earthquake is 1,000 times more powerful, 10 to the third, than a 5.0 earthquake. So now what we want to do is we want to look at the equations and see how we can write these inverse functions to the exponential functions. Let me share my screen with you and we'll get started. Now I've got some good news and some bad news for you. There's a lot of homework in this section. That's sort of bad news, but the really good news is most of these problems take very little work. So there's not a lot of time spent on these problems. So that's good news. The bad news is on the exam, there's not a lot of work to show. So there aren't very many opportunities to get partial credit. So you need to be very, very careful and make sure you're working these the correct way. So we're going to be talking about logarithmic functions, which are based on logarithms. So logarithm is L-O-G-A-R-I-T-H-M, and add an S for plural. Now, the relationship between a logarithmic function and an exponential function is given in this line right here. You see that we write the word log, which is actually an abbreviation for logarithm, and then we write the base. Whatever was the base of the exponentials, it's the same b that you see in the exponential. And again, it has to have the same restrictions as we had in exponential form. So the base has to be strictly positive and is not allowed to be 1. And we're going to write this below and to the right of log. Then even with the log, we're going to write the answer part. So this is going to be the answer part, whatever we came out with here when we evaluated the exponential. Now notice that what they've done here is they've swapped the x and the y because the logarithmic function is the inverse function to an exponential. And I'll show you what the graphs look like so you can kind of see the difference between the two. Remember, when you're looking for the one-to-one inverse of a function, you swap the x and y variables, and then you solve again for y. In order to solve for y, we have to create this new operation called the logarithm. So we have log base b of x equals y. Now, this is one of those rare times when the word of does not mean multiply. So when we look at this right here, if you had lined notebook paper, then you're going to write, oops, and I erased everything, so that doesn't help. All right, I'm going to write log. The b goes completely below the line to the right. Base b of x equals y. So it looks like that if you're writing on lined paper. I don't think you should ever do math on lined paper. It creates so many careless mistakes because you're trying to fit it within a line. Just switch to blank computer paper. Definitely, definitely better. But this is the format for writing it down. So when you see a logarithm, you actually think of it in sort of this reverse C letter. So what you're going to think of is you're going to think about taking this b and raising it to the power y and coming up with the answer of x. So this part right here is b for base. And the answer to the logarithm is actually the power or the exponent. So the logarithm is in fact the exponent. And then the part that goes next to the abbreviation log, that is the answer part from the exponential form, right? We should have a better name than answer part, but that's the only thing I've ever heard. So when we're looking at this, this is related to the exponential equation where we write b to the y power equals x. And again, we have the same parts. We have the base here, which is b. We have the power or exponent here, and this becomes the answer part. So these are, in effect, inverse operations of each other, just like multiplication and division are inverse operations, and addition and subtraction are inverse operations. Now we have the exponential and the logarithm, which are inverse operations. So if you see something that looks like this one down here, where you have log base b of c equal a, that means take the number b, strictly positive, not 1, raise it to power a, and get the answer c. That's what that means, right? So we're going to be writing this quite a bit today, hopefully to help you make sure that you keep it straight in your mind. So again, we'll see right here that this is our relationship. Y equal to the log base b, we always say base b, of x, but that of does not mean multiplication. There's no multiplication in there. It's just a symbol, is equivalent to base b to the y power equal to x. Now, when we're looking at these, what is our domain and what is our range? So how does this change things? Well, remember, this is coming from the same relationship in the exponential form. So the base b has to be strictly positive and cannot be 1. The x was the answer part. Now remember, if you take a positive number to any power, you can't get 0 and you can't get a negative. So typically, unless we've shifted it, that answer part is going to be strictly positive. So unless we've shifted or reflected it, the answer part is positive. Now, what about the power? In the logarithm, the y is the power. So the logarithm actually represents the power. So when we're looking at it and we're thinking about it, remember in an exponential, the power can be anything. It was negative infinity to infinity. And because we're swapping our x and y in these inverse functions, we're swapping our domain and range. So we're going to see that the domain is now 0 to infinity, and the range is negative infinity to infinity. So it kind of swaps out. Now let's move on, and I want to show you what this looks like. The book skipped this, and I think it's important to see the graph from the beginning so you can see the relationship. These are inverse functions. So I've graphed the equation right here, y equal 2 to the x, and for some reason it's not showing up here, so let me put it back on. This is y equal 2 to the x power. So I have y equal 2 to the x, and then I have its inverse function, y equal logarithm base 2 of x. So we have to be able to switch from one form to the other. Now, if I take this form right here, and I want to rewrite it into log form, remember that I have log, base, answer part. Well, how should I abbreviate that? I'll just put answer equals power. So this gets translated to log, base 2 below and to the right, y is the answer, and it equals x. Now, this is actually exponential form written in log form, but I want the inverse function. So I swapped the x and the y, and that will give me the inverse function, which is going to give me now, switching the x and the y, I get log base 2 of x equals y. This is the inverse function, and that's what I have graphed here. Now remember that inverse functions are mirror images across the line y equal x. Y equal x is the identity function because when you swap x and y, you still have the same equation. And when you take each ordered pair, 1, 1 swaps to 1, 1, 2, 2 swaps to 2, 2. And when you look at it and you fold it on itself, it is its own inverse. It's the only function that does that all three ways. Now, if we look at the blue graph and we look at the red graph, so the blue is our exponential, it has our normal exponential growth behavior. This down here in red is its inverse function, log base 2 of x. So what we did was we switched the exponential to log form. Then to get the inverse function, we swapped the x and the y. Notice that they are mirror images. If I fold this graph along the dotted purple line, the identity function, they will lay on top of each other. So this part right here lays on this part right here, and this part right here lays on this part right here, right? So you can see it's going down, approaching the negative y-axis as a vertical asymptote. The exponential has a horizontal asymptote. The logarithm has a vertical asymptote. Now, what else can we tell about these? When we look at the ordered pairs, notice that they're swapped. So 1, 2 on an exponential becomes 2, 1 on the logarithm. 2, 4 on the exponential becomes 4, 2. 3, 8 becomes 8, 3. 4, 16 becomes 16, 4. And those are the pairs of points that touch when you fold on that line. So this is what's happening. This is where the logarithm is coming from. It's coming from the one-to-one inverse function to an exponential. Now we want to talk about two special kinds of logs. There's what's called the common logarithm, which really isn't actually all that common anymore, although we do still have it around. For example, in the Richter scale for earthquakes, it is a base 10 system, which means that the logarithm is using base 10. So it's the inverse function to 10 to the x. And of course, it may be shifted or stretched or whatever. Now, this is what's typically known as a common log. And the old notation, of course, was to write it as y equals log of x. And you could skip the 10 because it was easier to use 10 in days before calculators and computers because 10 was easier to work with. We're a base 10 system. And so it was common at one time, but it's no longer common. We now have calculators and computers. And it turns out that E, Euler's number, that number we used with continuous growth and continuous compounding, that's a more natural base. That shows up more in nature. And so it's become the more common one. And we call that a natural log. And we'll see that in a minute. So if you write log and don't write the base, it's assumed to be base 10. But that's kind of gotten to be a no-no. So it's really better, quite honestly, if you write the base, log base 10 of x. Just make it clear, all right? It's a good habit to get into. And this, of course, is the same thing in exponential form of saying base 10, y power equals answer x, right? Now, what is this natural log? When computers and calculators became more prevalent, we could use more increased power. We used to have to look these up in tables, but now we can get the calculator or computer to do it for us. And this number E, Euler's number, 2.71828182845.9, blah, 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 goes forever, has no pattern, never repeats. So when we're looking at that number, it's a more natural base. Now, we could have written it as log base E of x equal to y. But mathematicians are notoriously lazy. If we can find a symbol that shortens how much we have to write, we're definitely going to do it. These became the most common ones around. And because they became most common and they're a more natural base for what happens in the natural world, how does population really grow? How do bacteria really multiply? How does the spread of diseases happen? Well, it turns out the best base, because these are continually happening, is base E. So because it's more natural, they call this the natural logarithm. And instead of writing log, we write ln, and we skip the base E altogether. We don't write it. The only base for ln is E. Anytime you see ln, the base is E, right? So writing ln with the base is like telling someone twice that the base is E. It's not necessary. Now, I like to make my L's cursive because otherwise, I don't know, that just doesn't look quite right to me. Somehow in text, it looks good, but when I handwrite it, I don't like it. So I tend to cursive my L and print my N and my X. And this, of course, is y equal the natural log of x. There's no base written, but we wrote ln, which means the base is E, the power is what the log is equal to, and the answer part follows the log to the base. And so we get x equals E to the y. Now, it turns out that E to the x and natural log of x are inverse operations of each other. So they're inverse functions to one another. Now what we want to do is go ahead and practice what we've learned by converting a bunch from one form to the other form. So again, there's not a lot of actual computation to be doing, but you do have to think very carefully about what the format is. So I'm going to write the format up here. So I've got log, below and to the right of the base, answer equals power. And in exponential form, this is base to a power equals the answer. These are the locations, all right? So I'm going to switch from one form to the other. So the first thing it wants me to do is switch log base 2 of 8 equal to 3. So I'm looking at this equation right here. So the base is 2, so 2 raised to the third power equals 8. Well, that's true. So I know I've done it correctly. Again, you're going in this sort of reverse C letter, like this backwards C notation. Now let's convert log base 4 of 16 equals 2. So again, I have base 4 to power 2 equals answer 16. All right. So I go in this counterclockwise backward C orientation. Now I'm going to convert this one right here where I don't have constants in all the locations. So again, I'm going base Y to the power X. So again, it goes by position. Between the log and the answer part is the base Y. On the other side of the log from the equal sign is the power, that's X, and it equals 2. So now I've got this one here. And now we're going to move on to the last one in problem number 2. Log base A of B equals C. So I start with the base, which is A. And you can tell that they don't always get them quite low enough in computer systems and stuff like that. It really should be lower than that. It shouldn't be even with the bottom of the O, it should be slightly below that. All right, so A raised to the power C equals B. Notice there's no work. This is good news because it's short. It's bad news because there's not a lot of partial credit I can give, right? So you want to be very careful. I would write this part that I have at the top of the page here in blue and pink. I would write this on your exam at the top of every page, all right? Make sure you have it at the top of every page. Make sure you don't mess that up. Now let's look at the next one. This is exactly the same. Write the following logarithmic equation in exponential form. So I'm switching forms. So base m to power f equals the answer 6, right? So let me write these again up here at the top. Log base of the answer equals the power. And in exponential form, the base raised to a power equals the answer, right? So when I'm looking at that, now the next thing I'm going to do is I'm going to convert this second problem here, problem number 4. So when I'm looking at problem number 4, I have base C to power F equals answer 6. That's it. That's all you're supposed to do. I know this seems too easy, but that's it. That's all you're supposed to do. Let's move on now to the next problem. So now we've got problem 5 and 6, which are more like problems 1 and 2, but now we're going from exponential to logarithmic, but we still need that relationship. So I'm going to come up here and I'm going to put in that relationship again. So let me see if I can get that to kind of fit up here a little bit. All right, so now I've got log base B of the answer equals the power, coming from base to a power equals the answer. So I'm trying to convert 9 squared equals 81. So the base is 9. That's not 10 and it's not E. So I have to write the base for sure. So I have log base 9, get the 9 well below, of the answer 81 equals the power 2, right? So the base is below, base below. The log is the power, log equals 2, and the answer part goes next to it. Now I want to convert this next one right here to logarithmic form. So I have 25 to the 1/2 power, which is really the square root, equals 5, which is true. The square root of 25, the principal root is 5. So the base is 25, which is not 10 or E. So I write log, then put the base below and to the right. The answer is 5, and the power is 1/2. All right, let's do the next one. So we have x to the 6th equals y. So my base is x. So I'm going to go by position, put x below and to the right. The answer part is y, which goes on the same level as log, and it equals the power 6, which is also on the same level as log in the answer part. Now we can convert a to the b equal to c. So our base is a, so we have log base a. The answer was c in the exponential, and the power was b. So hopefully this is making sense to you, and you'll be prepared to do some of these on your own in just a few minutes. So let's take a look at this one right here. So I'm again going to put in our little helper to help us remember how to do this. So I want to convert this to logarithmic form. Now it's in exponential because I can see the exponent, but this time the base is e. So that is Euler's number 2.71828182845 blah, blah, blah. Goes forever. So when I'm looking at that one, what I want to do is I want to use a natural log. Now, there are two ways that you can write it that I would take. I would take either one, but one of them is definitely preferred. So when it's base E, you just write ln and you don't have to write the base. Ln is always base E. The answer from the exponential was C and the power was K. So everything is written in a line. Now, I would also accept if you wrote it a different way, if you wrote log base E of C equals K, because technically this is correct. It's just more writing. Okay, so let's look at the one next to it. E to the F power equals 61 over 25. Again, because I have base E, I write ln of the answer part, 61 over 25, which the bottom of the 25 matches the bottom of the ln, and it equals the power, which is F. Right, this is going pretty fast. So let's look at the next one. Again, we're converting from exponential on the left to logarithmic form. We know this is exponential here, c equal 10 to the nth, because we can see the exponent. So putting it in logarithmic means we have to introduce log or ln. We don't have it currently, so it's not in logarithmic form. The base is 10, so you should think of this as the common log. It's no longer as common as it once was, but it used to be very common in the 50s and 60s. So you write log, you can skip writing the 10. If it's log and you don't write a base, it's 10. And then you write the answer part, which was C, and it equals the power, which is N. Really, though, I would strongly encourage you to go ahead and write the base 10. The only time I think it's a good idea to skip the base is when you have natural log. But natural log occurs more often than any of the other logarithms when you get into physics and engineering and other applications in business. And so it actually helps us save a lot of time in writing. Now, this next one has to be in logarithm form because I already see log, and next to it and to the right and below is 8. So I know the base is 8. So I'm going to take base 8, and then I'm going to raise it to the power -6, and I'm going to set it equal to the answer part, which is sitting next to the log, which is x, and that's it. That's all I have to do. Now, of course, I could simplify this and figure out what 8 to the -6 is, but I don't need to go through that. I could, but I don't have to. You could write it as 1 over 8 to the 6th, and 8 to the 6th is very large, so this becomes a very small fraction. Let's look at the next two. So let me put my helper up again so that we have the help. Now, we want to convert from logarithmic form, which you see here in problem 11, into exponential form. It has log, and it's written base J. So I know it's not base 10 and it's not base E. So this is going to give me J raised to the power 6 equals X. Again, base to the power equals the answer, this counterclockwise backwards C. Now, converting the one in problem number 12, I have ln. There's no base written, but I know if they put ln, the base is E. So I have E, and it's going to be raised to the power of 8, and it equals the answer part, which is X. Right? So hopefully by going in this backwards C, this counterclockwise notation, it will help you to get them on there correctly. All right, let me add another one. So we'll get our helpful device in here in between these two. Now this one says, use the definition of logarithms to completely simplify. So for this one, we may need a little bit more space than I allowed. So I'm going to move this down a little bit so that we have some space. Now, what does this mean, evaluate? Well, when they say evaluate, they're looking for a number answer. So when I'm looking at this, what I have right now is log of, well, what that looks like 10,000 squared. There's no base written. What is it? They wrote log, so it's not base e, but they skipped it, so it must be base 10. So the first thing I'm going to do is I'm going to put in the base of 10. So I have 10,000 raised to the second power as the answer. Now, I don't have the power right here. I don't have the power part, so I'm going to put in a power part. You can call it P for power if you want to, or X or Y or whatever you want to call it, right? So when we're looking at this, let's put this in right here. So I'm just going to call it X for whatever reason. All right, now we switch. When you're trying to evaluate, you typically don't evaluate in logarithmic form. You switch to exponential and then evaluate. So this says 10 to the x is equal to 10,000 squared. Okay, 10 to the x equals 10,000 squared. I need more space. I'm taking up too much room. Okay, so 10,000 squared. What's 10,000 squared? Well, it'll double the number of zeros. So instead of 4 zeros, I'll have 8 zeros. So this is 10 to the x equals 1, 2, 3, 4, 5, 6, 7, 8. So then I'm going to count backwards by 3 and put in my commas. What does that represent? Well, there are 8 zeros, so that must be 10 to the 8th. Do you see how I've written this so that in exponential form, I have the same base on the left and the same base on the right? Now, remember from our graph at the very beginning that both the exponential and the logarithm are one-to-one functions. So if these two sides are equal, then the bases are equal and the answers are equal. So the powers have to be equal. So x has to be 8. So the value of log base 10 of 10,000 squared is 8. In other words, 10 to the 8th power is 10,000 squared. Okay, let's look at the second one. Now this one has e to the natural log of 2. Now this is the one that confuses students the most, all right? So we're going to start and we're going to figure out what this one is. So the first thing we have here on the right, let me use a different color. I have e to the natural log of 2, and it's not equal to anything. So that's a problem right off the bat because I'm supposed to have a base, a power, and an answer part. And I have a base and a power, but I don't have an answer. So give it a name. You can call it A, you can call it whatever you want to call it. Don't call it B because the B is for base. I'm going to call it X. Just I can't think of anything else to call it. All right, X is, of course, the mathematician's favorite. Weeks. Well, this is exponential form, even though it has a natural log in it. Why is it exponential form? Because we have the power. Oh. So it's in this form right here. Let's try switching it to logarithmic form and see if that helps any. All right, so if I switch to logarithmic form, the base is e, so I can write ln. So I'm going to write ln, it's a base e. This is the answer. Oops, lost my n. This is the answer. This is the base. And this is the power, the natural log of 2. So I have natural log of x, that's the answer part, equals natural log of 2. Oh, well, the bases are both e, and the powers are the same because the logs are the same. Then the answers have to be the same. These are one-to-one functions. I think x has to equal 2. Now, why does this work? Let's look at e to the natural log of 2 in another way. Remember that the exponential and the natural log are inverse functions of one another. We swapped x and y, and then we resolved for y. So when we're looking at this, they undo each other. So if you multiply by 5 and then you divide by 5, don't you just get whatever number you started with? Yeah, you do. Take 7, add 2, 9, subtract 2, back to 7. Okay, start with 2 here. Apply the natural log to it. Okay, I've got some other number. Now exponentiate that. That undoes the natural log and gets me right back to 2. E to a natural log power, where they're back to back, the E and the L are side by side. You can't have a number or a constant here in front of the ln. These have to be touching. Then I just get the answer part of the natural log, just becomes 2. Okay, kind of crazy, but that's the way it works. Let's now look at the next part. So we're going to put our mnemonic device back in. Well, it's not a mnemonic device. It's just a helper to make sure that we don't forget the relationship. So when I'm looking at this one, oops, that's too far. Oh, it's not going to let me scroll too well. Okay, so when I'm looking at this one, I want to use the definition of common and natural logs to simplify. So let's start with what we have and then decide if we have exponential or logarithmic form. I have both e to a power and a natural log. So I have 3.41, natural log of 3.41, and then I have a plus 3. Okay, well, based on what I said before, what this e to the natural log of 3.41 is doing is I take the number 3.41 and I apply the natural log. Then I take e to that power, which undoes the natural log. Okay, so that just gives me 3.41. So this gives me 3.41 plus 3. That's it, which gives me 6.41 for the answer. That's it, right? Now let's look at this one next to us. This one is a little bit harder, I think. So when I'm looking at this one, I have log base 6, although you may think the first one is harder. Some students find that very difficult, right? So I have log base 6 of the square root of 6, and I want to evaluate it. Now, I need to have, this is log form. I don't have a base to a power. So, and I've got log written on the line. If ln or log is in the power, it's still exponential form. If ln or log is on the line, then it's logarithmic form. So I'm looking up here, I have a log, I need a base, an answer part, and a power. So when I'm looking at this, the base should be below and to the right. Okay, so this has to be my base. And then I should have an answer part next to the log before the equals. So this has to be my answer part from the exponential form. But the problem is I don't have this equal a power. So I'm just going to throw in a variable that will help me out. So this equals, well, we can call it x, you can call it z, you can call it whatever, Fred, call it Fred. Okay, so now I'm in log form, and typically if we're in one form, we try switching to the other to see if that helps us solve it. So what I'm going to do is switch. So I'm going to start here with the base of 6, raise it to the power of x, and set that equal to the square root of 6. Now, what that gives me is 6 to the x equals square root of 6. But remember, the square root of 6 is actually the 1/2 power. So this can be written 6 to the x equals 6 to the 1/2. The answers are equal to each other. That's what the equals means. The bases are both 6, then the powers have to be equal. They're one-to-one functions. Can't have more than one x belonging to each y, can't have more than one y belonging to each x. So this means that x equals 1/2. Now there's another way of thinking about this, which is going to get into properties of logs. So I'm actually working ahead a couple of sections, but this is actually a property of logs. I can write log base 6, and I could have converted this right here. And I could have written the square root of 6 and then equals x. This says 6 to some power equals 6 to the 1/2. 6 to some power equals 6 to the 1/2. Well, then the power has to be 1/2. And that makes it easy as well. Now, this is when you can get the answer part written as a power of the actual base. And then it just becomes whatever the power on the answer part is. So again, you don't have to memorize that now. It will be coming up in a couple more sections. All right, so let's look at this one right here. So adding in our helpful device, and I'm serious, write this at the top of every page. If you don't, you may make a mistake. So it really helps to write it in words, right? So when you're looking at this, it says evaluate the following without using a calculator. So I've got to apply logarithm base 2 to 1/8 first, and then add 2. The plus 2 is not a part of the logarithm. It's actually happening later, which means on the graph of the logarithm, I'm just lifting the whole logarithm picture up 2. That's what it is, a vertical shift up 2. So order of operations tells me to take care of this log base 2 of 1/8 first. Now, the fun thing about logarithms and exponential functions is there's no one right way to solve it. The nightmare thing about logarithm and exponential functions is there's no one right way to solve it, which means you can go several different ways. You should still come up with the same answer. So one of the things I might think to do, because I have more experience with it, is recognize that 8 is a power of 2. So I could use that property that I had in the last one, and I could rewrite 1/8 as 2 to the -3, right? And then I still have my plus 2, all right? So again, when I'm thinking about evaluating this logarithm part has to be completed first before I can add the 2. The plus 2 is an afterthought, so this is lifting the whole graph up 2. Now, the negative is because I lifted it out of the denominator, and 8 is 2 to the third, so it becomes 2 to the -3. So what does this mean? If I just look at this part right here, it says 2 to some power gives me 2 to the -3. In other words, if I just look at the logarithm part and I set that equal to x, then I know from this that 2 to the x equals 2 to the -3, so x equals -3. And then I can take that part and I can add it to the 2 to get the answer to the problem. So then I have -3 plus 2 equals -1. So the answer here is -1. Now let's look at the one on the right. The one on the right has a logarithm, but it's been multiplied by a 5. Now you know what this does to graphs, right? It's greater than 1, it's going to stretch it vertically, so it's going to go up faster, basically. So when I'm looking at this, I've got a logarithm, and it's being multiplied by 5. This is kind of a weird idea, but I want to foreshadow what we're going to see in a couple sections in logarithm properties. If I'm multiplying the log by a number, the log is a power. So the 5 is probably a power too, because I'm multiplying them together. And the 5 actually is a power. It ends up being the power on the answer part. So what are we going to do? How are we going to solve this? So let me switch colors here. So I have 5 log of 100 to the -3. Okay. Well, I've got log on the line, not in the power, but on the line. So it is in logarithm form. So I need a base, an answer, and a power. I don't have a base, but it says log, so it must be base 10. So I'm going to put a 10 here. Oh, I see 2 ways to go, so we'll work them both. All right, so one way to go is just to put equals x here, right? Give me something to go for. The problem is that the 5 is not inside the logarithm. In order to convert forms, it has to start with L. It can't start with a number. Okay, so method 1, what am I going to do? Well, I could move the 5, right? It's 5 times the logarithm. So if I divide by 5, that should work. So I get logarithm base 10 of 100 to the -3 equals x divided by 5. So this is method 1, right? Now that I have the logarithm isolated, I can switch forms. Oh, cool. Although this doesn't look so great. I'm not too thrilled about this. It's looking kind of hard. Okay, so I'm going to start with the base 10. Power is a fraction, x over 5, but that's still a line, right, with slope 1/5. And then it equals 100 to the negative 3. So when I do this, I have 10. My power is x over 5. So make sure you get it all up in the power. Sometimes computer programs and books, they get it too low. It doesn't look right. Get it up there. No part of the 5 should be touching any part of the 0 in the 10. And then this has to equal 100 to the negative 3. Well, I know 100 is a power of 10. So I'm going to rewrite 100 as a power of 10, use my exponent rules to combine them. And then I'll have two sides as powers of 10. And then I know, because they're equal, that the powers have to be equal. So 100 is 10 squared, and it's being raised to the negative 3. So over here, I have 10 to the x over 5. Well, 1 base, 2 powers, you multiply the powers. So this becomes 10 to the negative 6. And this is 10 to the x divided by 5, right? Sometimes you'll see them written with slanted sideways fractions because they're having trouble getting it up there. This is why you use blank computer paper to do your work. Don't use lined paper. You can't get that into one line. And I'm going to need more space. Let's see if I can hit return. Yeah, that works. Okay, that gave me enough space. All right, so what's the next thing? These are equal and the bases are equal, so the powers have to be equal. And if x to the 5th equals negative 6, then I can multiply both sides by 5, and I get x equals negative 30. Whoa, okay, well, I wasn't expecting that, but that's what it comes out to be. Okay, well, what's method 2? What was the other way I thought to solve this one? So let's do this one in red. So I have 5 log base 10 of 100 to the negative 3 power equals x. Well, the first thing I thought of was, let me just take out this logarithm and evaluate that separately. And then once I've evaluated that, I can replace the logarithm with that value. So I'm going to come over here and I'll do it in gray. So I have log base 10 of 100 to the negative 3. Now, I don't want to use x because I've already used x for something else. So let's use p for power. That works. All right. So this equals p for power. And the p is on the line. It's not written in a power position because the log is the power. It brings the power down to the line. All right. So, I see 2 ways to go from here. One is 100 is the power of 10. So I could convert it right here. So I have log base 10 of 10 squared to the negative 3, which you know is going to give you 10 to the negative 6. So I have base 10 of 10 to the negative 6 equals some power. This basically says, if you take 10 and raise it to a power, you'll get 10 to the negative 6. What's that power? Well, the power is negative 6. Okay, so I'm going to take this part right here and replace it with negative 6. And again, I get x equal negative 30 for my answer. Same solution. Multiple ways to proceed, all correct. You use the one that makes the most sense to you, but is still mathematically correct. All right? I'm not going to take off if you use a different method than I used. My job is to figure out if your method is mathematically correct and give you credit for it. All right, let's take a look at problem 19. We are zooming through this. So now we've got some others here. We want to think about what this means. We're about to get into yet another property of logarithms. So this will be the 3rd property that we've seen today. I think there are 8 total or something like that. I lose track of how many, but about 8. So when I look at the natural log of 1, it wants me to evaluate it and not use a calculator. Now you can use calculators for natural logs, but we always do it by hand if we can get an exact answer, and we don't use the calculators. On the calculator, ln is the natural log and log is base 10, right? And you'll see that above them, the second function is e to the x, the inverse of natural log of x, and 10 to the x, the inverse of log base 10 of x. So starting with the first one I have here, natural log of 1, evaluate it means find the power. I know the base is e. I know it equals a 1. I need that power on it. So I'm going to come up here. Well, actually, let me come down here. Let me add in our helpful part. So I'm just going to put equals x. Okay. The base to the power equals the answer. So this is the same thing as writing e to the x equals 1. What power can you raise about 2.7182818284592 and get a 1? Well, unless the number is 1, the only power you can raise it to get a 1 is 0. Ooh, this is a property of logarithms. When the answer part is 1, the power is 0. So let me write that down. When, oops, erasing and writing doesn't work too well. When the answer part equals 1, the power, the logarithm itself, equals 0, right? So this tells me that x equals 0. So the natural log of 1 is 0. What about the next one? It says log of 1, not ln, but log of 1. So log base 10 of 1. Well, is that going to make any difference? Well, let's see. Let's write it out. So we have log base 10 of 1 equals some power. That's the same thing as writing. Maybe I shouldn't use a slash. A little squiggle in between. This says 10 to some power equals 1. Well, the power has to be 0. So no, it doesn't make a difference. And this is a property of logarithms. It doesn't matter what the base is. When the answer part is 1, the logarithm equals 0. The power is 0. So this next one that we have, log base b of 1, it's a 0. I don't even have to think about it. Answer part is 1. The logarithm is 0. Now, what about this next one? This next one is a little bit different. This gets back to what I was talking about previously, a different property of logarithms, and we have a log of 10. Now, it doesn't have the base written, but it wrote log, so we know it's got to be base 10 equal to x. Well, this basically says 10 to some power equals 10. 10 to what power? 10 to the first. Well, then x equals 1. Right? What about the natural log of e? We're going to see that this one is very, very similar to the one that we just did. So when we look at this next one, and I'm running out of space, I have natural log of e, and I don't know what it is, so I'll say equals x. This is the same thing as writing e to the x equals e to the first. Well, again, x has to equal 1. So again, this is saying that when the answer part can be written as a power of the base, then the power is just that power on the answer part, the same as the base, right? We only have one problem left, which is to evaluate this without using a calculator. Now, it's written in common log, so we have 2 log of 100 to the negative 4. We don't know what it equals. We know that we need to have some kind of power on it. So here's our device. It's in logarithmic form. So we can see right here, we need a base, an answer part, and a power. We have a base, it's not written, but it's understood to be 10. So we can write 2 log base 10 of 100 to the negative 4 equals, well, I need a power, so I'm just going to throw in x or p, whatever, it doesn't matter. Now, what about this 100 to the negative 4? I know 100 is a power of 10. So I'm going to rewrite 100 as 10 squared, then raise that to the negative 4. 1 base, 2 powers. Exponential rules tell you that you will multiply the powers. So this gives me 10 to the negative 8 equal x. Now it's tempting to say, oh, well, then it's negative 8. But the problem is this 2 that you see right here out at the front. So whatever we get out of the logarithm, it's going to double it. Now you could divide by the 2 and then evaluate using exponential form, or you can use the property of logarithms that says this part right here is going to be a negative 8. And then I can take the negative 8, multiply by 2, and I'll get negative 16. Let's see if it works out the same if I use exponential form. I've got to move the 2 because it's not a part of the logarithm. So I get log base 10 of 10 to the negative 8 equals x divided by 2. So this tells me that 10 to the x divided by 2 power equals 10 to the negative 8. And since they're equal and the bases are the same and they're one-to-one functions, then I know the powers have to be equal. I get x over 2 equal negative 8, multiply both sides by 2, and I get the same result, x equals negative 16, right? So I hope this has helped. In our next section, we'll be looking at the graphs of logarithmic functions in more detail, and then we'll get back into the equations for logarithms and exponentials when we have more complicated expressions in the base, answer part, or power. And we'll look at how to solve those. I hope you'll join me for those videos.